In this video, we're going to continue our conversation on air conditioning troubleshooting, and we're going to talk about non-condensibles, inefficient compressors, and low and high ambient temperatures. Now I'm going to let's start off with the temperatures, because those are a lot of times the most frequent issues we have. Low ambient air temperatures, especially like if you're running air conditioning on what I call the shoulder seasons, where it's still low temperatures outside but a little bit warmer inside, especially happens in a lot of commercial buildings where they run air conditioning year round. The low ambient temperatures will cause a low head pressure because of excessive heat transfer between the condenser and the ambient air. The low head pressure reduces the flow of refrigerant through metering devices. The reduced refrigerant flow starves the evaporator and causes low suction pressures and high superheat. Less refrigerant moving, lower pressures, means less work for the compressor, and the amperages will be lower than normal. You can resolve this issue with low ambient controls. Low entering air temperature, low suction pressure, low discharge pressure, high superheat, low amp draw, and high subcooling are all signs of this condition. And on the opposite side of the problems, we have high condenser entering air temperature. The hotter the day, the more frequently this issue occurs. The higher the ambient temperature around the condenser, the less of a temperature difference for heat to be rejected. Remember, heat flows from hot to cool, but at a rate that is proportional to the temperature difference. The larger the temperature difference between the condensing temperature and the outside air, the more heat will dissipate. When heat is not rejected from the refrigerant, it continues to accumulate in the refrigeration cycle, and pressures will continue to rise. In reciprocating compressors, the high pressure reduces compressor efficiency because of the clearance space at the top of the compressor pistons. High head pressure also will elevate the liquid temperatures as it enters the metering device, increasing the flash gas and decreasing the net refrigeration effect. The suction pressures may be a bit higher as well. The system will have a hard time maintaining temperature and humidity of the conditioned space. So as I've said in another video, you have to remember that the high outside temperatures will decrease the efficiency of a system, so it's very important to look at what the design specs are. Couple thoughts on metering devices, okay? Evaporator superheats are very dependent on metering devices. Cap tubes or any fixed metering device is dependent on the pressure difference across it. The higher the pressure difference, the more refrigerant will flow and will lower the condensing, subcooling, and evaporator superheat. So be very careful on the pressure differences between the high and the low side if you have fixed bore metering devices. TXV systems will try to maintain the evaporator superheat, but at the highest ambient temperatures, when you have a high temperature condition, the pressure may be outside of its control range. You may see normal condenser subcooling, while the TXV is not able to maintain evaporator superheat. So again, just be aware that your evaporator superheat, the operation of your TXV, the operation of your fixed bore metering devices is very dependent on that pressure difference between the high and the low sides. Now, the next line, we get outside of the temperature issues we see with condensers, and we look at non-condensibles. Non-condensibles most often are air or water. The reason they're called non-condensibles is that they will not change state under normal operating conditions from a gas to a liquid or from a liquid to a gas. Non-condensibles enter a system through poor service practices. Unless the system is an ultra-low pressure chiller or pump-down systems, non-condensibles will not enter a system through a leak, as the pressure inside the system is greater than the pressure surrounding it. Now, if a system is empty, doesn't have any refrigerant in it, okay, it means there's a leak in there, everything's leaked out, and yeah, you're going to have air in the system. But through normal operation, non-condensibles will not enter the system through a leak unless it's ultra-low pressure chiller or a pump down system, because the pressure in the system is always greater than the air pressure. A technician forgetting to purge hoses can let air or water vapor into the system. The air and water vapor will pass through the evaporator and compressor because the compressor is a vapor pump. The air will remain at the top of the condenser and not condense. The subcool liquid seal at the bottom of the condenser will prevent air from passing out of the condenser and continuing through the refrigerant cycle. The air and water vapor will continue to take up condenser surface area, causing the pressures and temperatures to rise. If you get enough air in a condenser, it will actually block the tubes of the condenser. Subcooling will be high because of the high head pressures cause a greater temperature difference between the liquid temperature in the condenser and the ambient air surrounding it. Again, the larger the temperature difference, the faster the heat flows out of the condenser into the ambient air. Non-condensibles in a system and an overcharge of refrigerant have very similar symptoms when a TXV metering device is used. So symptoms of non-condensibles include high condensing head pressures, high subcooling, high compression ratios, high discharge pressures. The easiest way to see non-condensibles is to actually watch your pressures when your system turns on. You start your system when the system is at an equilibrium between the low and the high pressures. Your non-condensibles will cause your high side pressure to shoot up drastically. Sometimes they will pulsate as the refrigerant and the non-condensibles cause a seal against each other. To resolve non-condensibles, there's only one way to do it. Recover all refrigerant, evacuate the system to 400 microns or better, and recharge. Always purge your hoses or use stub-type gauges to avoid this issue. The shorter the hose, the shorter the fitting that you have on the access valves with your gauges, the less chance of non-condensibles getting into the system. The days of the long hoses are basically over for a lot of these systems because you can actually have more non-condensibles in your hoses than you do in some of the refrigeration systems out there. Now finally we can get to the topic of the inefficient compressors. I cover this topic last because it is the most frequent of the problems that we've discussed here. Inefficient compressors are most often caused by leaky valves or worn piston rings. Symptoms of inefficient compressors are high suction pressure, low discharge pressure. Think about that. If a compressor's not pumping properly, it's not going to pull a suction and it's not going to pump that out to the discharge. So your pressures will be closer than normal. Low compressor amp draw, it's not doing a lot of work. High superheat for a cap, tube, or fixed orifice. On a TXV system, it might adjust its superheat and it might act normally. High return air temperatures. You're going to have condenser subcooling issues. And more importantly, you're going to have a low outdoor temperature split. That's your condenser air temperature. The difference between the incoming air, that's the ambient air around the condenser, and the air coming out of the top of it will be much lower when you have an inefficient compressor. We're not rejecting as much heat. So your system's going to be running, but it's not going to be running at peak efficiency because of this. And again, this is most often with a reciprocating type compressor. Because of the fact that scroll compressors do not have pistons, it's less frequent with the scrolls. Now, if you're working on a heat pump system, I don't have a slide in here for this, but if you're working on a heat pump system, be very careful that your diagnosis of inefficient compressor is not a reversing valve problem, because sometimes it does look the same.